in these early galaxies, which we now can observe, these early galaxies are so dusty that the stars are basically invisible at visible light, and their light is thermalized down to approximately 20 K by the dust that is enclosing the galaxy as it forms. When the galaxy gets to about 200 million years, the dust has condensed into the disk, and then you can see the stars. So what happens is we get thermal energy thermalized down to about 20 K. Well, how is it thermalized and isotropized all the way down to 2.7 K? What we see in this plasma process is at the center of galaxies, these currents converge and they kink up to form plasmoids. Now, plasmoids we observe routinely in our experiments at our laboratory, which I'll discuss in the afternoon, are self-contained, magnetically confined objects. So the currents moving through the plasmoid create magnetic fields that confine them into a little ball. Instabilities within the plasmoid create beams of ions moving in one direction and electrons moving in the other direction. And this is a very good quantitative model for things like Haro objects, active galacti, nuclei, and quasars. You don't need any gravitation to form these objects. So these filaments are quite important because we can predict, again, simply by electromagnetism, that these filaments will form a downward hierarchy of extremely dense magnetic filaments that go out into the universe and have the ability to absorb and re-emit microwave frequency radiation. So you get a microwave fog, which is what isotropizes and thermalizes the cosmic microwave background. And again, for decades, we've had proof that this fog exists, that the universe is not transparent in radio frequencies. Because there's a correlation between the infrared and radio waves produced by ordinary galaxies. It's not a linear correlation, but it's quite a good correlation. And if you look at galaxies in our neighborhood going out to about 600 megaparsecs, so this is too close to us to be accounted for by any sort of cosmic evolution. This is only a billion years ago. What you find is the further you go away from Earth, the less the radio radiation for the same infrared luminosity. And this drops by a big factor. This is a factor of approximately 10. So unless you want to accept that the Earth is in a very exceptional spot, you have to accept that there is absorption going on and re-emission of radio waves into the microwave radiation background. And another proof of that, by the way, is what I mentioned in my earlier presentation, this recent discovery of this 300 trillion electron volt photon. If the density of the cosmic microwave background is linked to the density of matter, then as you go out into space, you have a lower temperature for the cosmic microwave background. We can't see that lower temperature because the temperature around us is 2.7 K, and we're looking at a semi-opaque object. Again, from actual observation, this is a much more consistent explanation of the cosmic microwave background than saying that it was produced by this multi-trillion degree fireball long ago.
Our videos come out of LPP Fusion's research in fusion energy, which will power a future with abundance for all, with a clean, sustainable economy and environment. Goods, housing, and infrastructure would be extremely affordable once fusion kicks in. Fusion energy is the key to an advanced future. Support fusion research. The link's in the description, and thanks.